Eda, mi devi dire se ci senti. Pronto? Hi, everybody. I think it's time to start. And okay, because we have something to share with you. And first of all, the aim of this presentation. It will be on the Advanced Training Programme. And this webinar introduces a specific module of the Advanced Training course. This course represents an excellent opportunity for those who wish to explore topics ranging from digital technologies to artificial intelligence, cybersecurity, and more. Within this module, we will briefly present the themes of digital modeling, which will be addressed in depth by several lecturers from different universities in Module 5 of the course. The Advanced Training course is organized by the partnership of the European project VIC, we say VIC in Italy, and is open to everyone. Information on registration procedures and a detailed course description are available on the project website, Virtual Immersive Consortium. I think we can start. I will start with a short introduction, and then I will leave the floor to Vasily Manfredi that will follow with the second part of the lesson. My part will take only some minutes just to tell you what we are talking about. In this specific webinar, we will focus on modeling, not only on what modeling is, but above all, on how modeling is not an end in itself, not a form of art, or not only, quite the opposite. We will explore what modeling is actually used for example, in the industrial domain, and which type of industries benefit from it. In fact, the earliest form of modeling originated precisely within the industrial sector. Since the 1950s, since the early of the 1950s, modeling has evolved starting from a mechanical and precision manufacturing, focusing on accurate models for the production of mechanical components. In the 1950s marked the emergence of the engineering CAD, a foundational area in which digital modeling first entered engineering, aerospace, and defense industries. In this early stage, the model functioned primarily as a mathematical geometry, serving as a precise digital description of physical forms. Engineers leveraged basic computational tools to perform calculation with greater accuracy, relying on the model as a medium for representing complex curves, surfaces, and technical specification. These geometric models played a crucial role in advanced precision manufacturing and fabricating aerospace components with improved tolerance. From the early 1970s, companies such as Boeing, General Electric, General Motors, Ford, Fiat in Italy, in Europe, especially in advanced machine centers and prototyping, benefited significantly from the use of CAD and digital modeling, including faster prototyping of engine and transmission components, standardization of quality, reduced dependence on highly specialized labor for each individual machine. During the 1970s, digital modeling transitioned into CAD/CAM area, where digital design became directly linked to computer-aided manufacturing. This milestone positioned the model not just as a representation, but as a driver of real-world fabrication processes. In manufacturing and automotive sectors, CAD/CAM systems enable seamless transfers of geometric data from design environment to CNC machines, profoundly reducing manual intervention and human error. The digital model now controls tool paths, machining sequences, and fabrication cycles, establishing a continuity between virtual designs and physical production. The automotive industries benefited from this integration, enabled faster prototyping and more intricate component geometry to be produced reliably. This decade introduced the paradigm that the digital model could act as a bridge between conceptual design and industrial execution, setting the stage for future intelligent manufacturing systems. In the 1980s brought a significant evolution in digital modeling, with a widespread adoption of 3D surface modeling, particularly in automotive and product design industries. And we will speak later a lot of this. Designers could now manipulate free-form surfaces to create complex, aerodynamic, and aesthetically refined shapes that were previously difficult to achieve through manual models. This new capability elevated the model from a tool of a geometric precision to a medium of expressive and performance-driven form development. Automotive manufacturers used advanced surface modeling to refine vehicle bodies for improved aerodynamic safety and visual appeal. In the 1990s, parametric design revolutionized digital modeling by introducing rule-based and relational systems that allow designs to define geometry through parameters rather than static forms. This paradigm shift was particularly influential in advanced architecture, that is our main field of interest here in Politecnico, where complex geometries and adaptive forms became achievable through algorithm logic. Parametric modeling allowed users to embed constraints, relationship, and behavioral rules within the model, enabling form to adjust dynamically as parameters changed. Architects embraced this approach to explore responsive geometries, facade systems, and structural form driven by environmental, spatial, or material criteria. Parametric tools enable unprecedented experimentation with variation, optimization, and generative design workflow, helping bridge conceptual design with structural rationalization. As a result, the 1990s established the digital model as a system capable of generating form through relationship rather than mere geometric drafting, influencing the evolution of computational design that continues today. This is one of our field of interest. The 2000s saw the rise of BIM, Building Information Modeling, a transformational shift in the role of the digital model within the construction industry. BIM expanded the model beyond geometric or rule-based data into a fully information-rich environment containing metadata, materials, schedules, performance data, and life cycle information. This evolution redefined the model as a collaborative platform where architects, engineers, contractors, and facility managers could work from a single integrated digital source. The BIM model acted as a coordination hub, enabled clash detection, improved communication, and reduced construction error by synchronizing disciplines in real time. Entering, and we are going into the second part of the communication. This was a short view on what we will deal with. Entering the 2020s, digital modeling evolved into immersive and cognitive system powered by XR, extended reality, and artificial intelligence. In production, training, and decision-making environments, these models function as interactive interfaces that allow users to visualize, manipulate, and understand complex information spatially. XR technologies such as AR and VR provide immersive environment where workers can perform simulation, view digital overlay on real-world equipment, and participate in collaborative virtual workflows. Meanwhile, AI enhances the model's ability to analyze data, predict outcomes, automate processes, and assist human decision-making. In combination, XR and AR transform the digital model into an adaptive system capable of guiding users, responding to context, and supportive collaborative problem-solving across distributed teams. These emerging tools redefine the model as a cognitive partner rather than a static representation, creating big and new opportunities for enhanced learning, operational efficiency, and real-time decision support across industrial and architectural and design domains. I leave the floor to Vasily that will introduce you to a more interesting part.
Hi, everyone. Hope everyone is okay. We just live changed, and I'm Vasily Manfredi. I'm a PhD candidate here in Politecnico, and I will introduce you to two main subjects. One, it will be more for a common ground, so it will take place on illusions, how like 3D is just born, and then how it developed around the years. And later on, we will have a little bit more specific part also on 3D modeling, rendering, and all other things. So let's start with these two images that are separated by 33 years of technological development. On the left, we can see 1977 Star Wars poster, and on the right, a frame from Inception in 2010. Both are completely fabricated, and both were made through technical crafting. Still, when most people encountered them, both of them, in cinema, on screens, on Netflix, the reaction is always like a belief, you know? It's not a reality analysis. So it's something closer more to genuine belief. This is the main problem that the field of 3D visualization and visual effect has been working on for over 50 years. Not just how do we make images, but how do we make images that could be believed as real? Images that produce in the viewer the experience of seeing something that doesn't exist. So the question is what this first part of presentation is about. So the technical content that we will cover, geometry, materials, rendering, optimization, all of them exists in service of that single goal, make people believe in every sector. So today we will trace the arc from the physical and crafted techniques of the early cinema's movies to the mathematical, computationally produced imaginary that now we work on. So I think a lot of us will recognize this animation. This is a frame from The Empire Strikes Back from the 1980s. We can see the AT-AT Walker during the hot battle sequence, and it were stop motion models. All of them were handcrafted. Those are physical miniatures reposition it between each photographic exposure, so each frame. Understand why the actual snow were made of baking soda, so it stood up as the snow. And the cockpit that you see is actual real physical construction. So every switch, every panel, every light was actually there in front of the camera. But how they made it? Here, it's very significant to highlight the logic behind this approach. Because before the digital tools, creating a convincing visual illusion required building, let's say, an intermediate physical reality, something that actually existed in the space that a camera could photograph, so could picture it, that obeyed the laws of optics. So the gap between what the audience saw and what actually existed was bridged by physically constructing something. So in this case, the AT-AT. So the digital three-dimensional production later on eliminated that intermediate step in some cases. Still, on current movies, we still use physical VFX. But now what we now construct exists as a numerical description, so exists in a three-dimensional space. So the perceptual result, something that the audience experience of something special present, materially real, can be, and it's best, identical to what was achieved with physical model. So the photorealism. In here again, Star Wars. I think you can see that I'm very passionate about Star Wars. So in the original trilogy, Star Wars trilogy, every lightsaber effect was produced by rotoscoping. So an artist painted a glowing line directly onto the film, frame by frame, but every frame in every sequence where the weapon, where the lightsaber appeared. So in total, 300,000 frames by hand. So that's not for the drama, actually, but it can reveal what the relationship was between the technical tools and the creative intention. So the desire to represent an impossible object convincingly, a lightsaber in this case, existed long before any computational tool could reproduce it, let's say, in a photorealistic way. So the approach was extraordinarily labor intensive, a lot of time consuming. So this is the constant that connects the rotoscoping artist from the 77 to the rendering engineers today. I mean, the tools have changed beyond recognition, but the goal, still producing a perceptual conviction, hasn't changed at all, after all. So let's go to the birth of three-dimensional modeling. The history of 3D computer graphics as an actual serious technical field began in the early 70s, primarily at the University of Utah with Sutherland and Evans. So on the left, you can see an image, an end. It was Edwin Catmull Clark. Actually, Clark, it will become later, but it's just Ed Catmull, let's call him, in the early 70s. And that's a rendered hand, one of the first demonstration of 3D surface representation in motion into three-dimensional form. Catmull later will found Pixar, that we all know Pixar. His work introduced texture mapping to three-dimensional meshes and has a main contribution that remains central to the field today. Instead, on the right, we can see characters from Tron of the 82. It was the first large-scale commercial use of CGI in a movie. The total cost was around $4 million. So let's imagine in the 80s, $4 million for a 20-minute screen time. So it was a big cost. And also it was let's say, there was a lot of skepticism, because during that time when it was projected, not a lot of people knew what was a computer, what was a pixel. So actually that movie flopped, but there was a major demonstration of three-dimensional rendering into movies. So also two milestones that marks real qualitative shifts. We can see it here. 91, Terminator 2, the T-1000, that is the bad guy here, was the first photorealistic computer-generated character that was successfully integrated into a live-action theatrical footage. It was the first time that mass audience encountered a fully digital object that they couldn't immediately identify as one. So that was a pretty huge technical achievement, because it wasn't just an image quality frame. It was a perceptual integration of synthetic and photographic elements. And here we can say that they used the actual weapon, the fire weapon, to make the perceiver, the viewer, believe it as real. On the right, 95, Toy Story, the first fully computer-generated theatrical feature. So the first completely computer-generated movie. Every element, every frame produced was produced computationally. That was the proof that CGI could carry feature-length narrative cinema. So 23 years separate Catmull's hand, rotating hand, from Toy Story complete synthetic world. That rate of development, not just in level of quantitative improvement, but real qualitative steps, has continued to the present day. We can also think that Toy Story, the movie, it required 800,000 of computational calculus. And that's pretty funny, actually. Pixar's computer was so loud that the artists that were working on this movie, they had to have noise-canceling headphones to keep working. That was quite a lot. And also, every frame required around 45 minutes of rendering. So today, it's quite different. So how it works. Here, what we're looking is that the fundamental primitive, a sphere that could be also a point, a vector of anything, in three-dimensional space is defined by three numbers. So its position on X, Y, Z. And from that geometry, we can create different kind of geometries, very articulated kind of geometries. So it's an ultimately collection of those kind of points, and are organized according to specific connective rules with material, lighting, properties to make them feel real, photorealistic, and uses them into movies or cinema and video games. So this kind of modeling, it's anorganic modeling. Then you can add bones to make it move into the three-dimensional space. We will see it later how it actually works. Here, it's just a glimpse for everyone that from a sphere, we can actually build something incredibly hard and specifically very, very technical. Then we have the rendering part. So once the shape is modeled, as we saw before, it needs to be given the light. Rendering is the process that calculates how light behaves on the surfaces. So in the early years, everything was approximated. Then, let's say, ray traced arrived. So each pixel simulate light arrays, bouncing as they do in reality. Today, we only use, I mean, it depends by the use, but us in Politecnico, we usually use PBRs, that's physically based renderings. materials and reflection follow the true law of physics. So let's say this, sorry, because I'm watching the time and I don't want to, there's a lot to say and I would like to say everything, but I have to cut a little bit. So for decades, rendering required time and computing power. But today, with real-time engines like Unreal Engine, light is calculated instantly. Here we can see two different parts, an ad and also the Mandalorian in the first part of this GIF. The Mandalorian was filmed inside an enormous LED room, and the environment were projected live. The actors could see the world around them, which helps a lot, and the reflection were actually real, not added in post-production, and also so it cost a lot of the costs. So this enormous LED room, it's called the volume, and it's used by ILM, which is Industrial Light and Magic, founded by George Lucas, Star Wars again, is 6 meters tall and 21 meters wide, and it's made up of over 1,300 LED panels. And something that it's really cool is that Fortnite and The Mandalorian uses the same graphic engine, so we can see the scalability of the engine. Also, we use it 3D in simulation, so 3D is not just only used to create shapes, but also behaviors. Water, smoke, fire, fabrics, all of these and more. All of these are simulated using real physics laws. Artists, engineers use the mathematics of fluid to create poetry of movement. So the black hole of Interstellar was actually calculated using equations, and then it was published. So we can see how that movie can be transferred into publications. So today, what are we using? Today, let's say, back in the days, only Hollywood could afford incredibly realistic 3Ds, VFX. Today, instead, anyone with a laptop can make, let's say, a film or a photorealistic or a character. Blender and Unreal Engine in this case are free and powerful, with a little bit of study, obviously. Even a common persons can recreate cinematic level effects. So this is, let's say, a revolution of access. Blender is maintained as a non-profit foundation and donors, such as Epic Games. And also NASA and ESA use it for its scientific visualizations. We'll have a little bit of tomorrow also. Artificial intelligence is, I mean, we all see it, it's transforming everything, hopefully in good. And now we can generate faces, environments, animation in just a few seconds. And I mean, artists are not becoming less creative, but faster. We can move more freely. We are entering in an era where ideas can take shape almost instantly. On the left, we can see a MetaHuman tool that creates a completely realistic face in less than, let's say, 20 minutes if you're a very skilled artist, but it's pretty easy to use. So now I want to go to the second part and explain more deeply, more in depth, what I just showed you right now. So what is a 3D object? A 3D object, every 3D object exists in a coordinate space defined by the three orthogonal axes. X encodes width, Y encodes depth, Z encodes height. This axis, the position of any point, it just tells the position of any points in the space, and it's fully described by those three numbers. It displays along each axis from the origin. So this is the geometric inscription of a 3D model. So every vertex in every mesh, in every 3D application is exactly this, 3 numbers. So Z, Y, and X. So by understanding this coordinates framework and understanding how objects are positioned and oriented through transformation matrices, it's the main starting point for working effectively in any 3D context. But still, what is a 3D object? 3D-dimensional objects are built from 3 main interdependent elements: vertices, edges, and faces. Vertices are points in the 3-dimensional space. Edges are lines, segments connecting 2 pairs of vertices. And faces are polygons defined by closed loops of the edges. So there. The simplest case is a triangle, obviously, and then there are the 4-sided faces. So the way that these elements are organized and connected, it's called their topology, is separated from their spatial position, their geometry. So topology describes connectivity of those. Geometry describes location. This distinction matters significantly for operations like subdivision, so creating more smooth operations, deformation, so changing the actual form of the 3D object, and UV unwrapping, so giving to the 3D object an actual material. So all of which depend more on how a mesh is organized in its topology and on where its vertices are. So still, what is a 3D object? A mesh is the network of polygons that defines a shape surface, as we said. So here we can see the comparison that shows that the same object represented with a triangulated mesh on the left and a quad dominated mesh on the right. So the quad, they have different use scenarios. The quad mesh has organized rings of edges, edge loops, that follow the form of the surface. This organization matters. Quads are subdivided cleanly and predictably, and they deform in a controlled way. So when a character moves or bends, we can actually predict how it will move or bend. Triangles actually don't have this property. So when you see in a video game a smooth movement, that mesh was computed by the artist in a quad dominant mesh. Then it will be triangulated by the GPU, but it's a later process. So the practical consequence is use quad topology, the quadrilateral topology, when modeling characters or anything that will be animated, and use geometry that is triangulated for real-time deployment. So as said, GPU processes triangles mainly. So still, what is a 3D object? 3D object has different parts, and here we can see the normals that are defining in which direction a face points. Also edges and vectors. Here we can see different kind of normals, so from faces and vertices. So a vector, a normal is a vector that is perpendicular to the surface at each point, and it's pointing outward from the enclosure volume. So why this matters? This matters because it's a critical for a correct lighting. When we see in movie, video games, etc., always consider all the 3D objects that your mind can conceive. So when you render an object, so you compute actually that object, the renderer uses this surface normal at each point to calculate the angle between the incoming light and the surface. So it determines how much light that surface reflects on how it interacts with that surface. So let's imagine those are right normals, so they're good. Let's imagine them flipped, so they're not good anymore. They're pointing inward rather than outward. So the surface will actually appear dark, or in some cases, like in video games, or while you're using Unreal Engine, Unity, it will just appear invisible from the outside. So regardless of how well the materials and lighting are set up, you will not see it if the normals are actually flipped. So flipped normals are among the most common artifacts when importing geometry from, let's say, CAD systems or photogrammetric reconstruction pipelines. So recognizing them, it's very, very important. To fix them, it's a lifesaver and a basic diagnostic skill that will help you a lot later. So still, what is a 3D object? A 3D object also has the origin point, which is the object anchor into the three-dimensional space. It's the point, let's say, around which rotation, scale, transformation are applied, and the point that corresponds to the zero position in the object local coordinate system. Here, it's important to clarify that there's a local coordinate system of the object, and there's the world coordinate system. So we will use both. Getting this right matters practically, because if the origin is placed incorrectly, which still it's pretty common in photogrammetric reconstruction, where the reconstruction software places it in its arbitrary point, the object will rotate around the wrong point, because that origin point, if you rotate the object, will keep that point to be like rotated. Uses also wrong scales, wrong center, land in the wrong position. I mean, it's a nightmare. So it's always good to have it positioned, placed in the point that you want. So repositioning, it's something, let's say, semantically meaningful. It's the geometric center and define also the floor of the contact points. It's a standard pre-processing in any optimization pipeline, so it's pretty important. So now we can go further, and let's start on, let's see different modeling techniques. There's here a polygonal modeling that directly manipulates vertices, edges, and faces, the one that we just saw, to build and refine or define a surface mesh. This is the foundational approach in 3D production. It's the method most broadly applicable across domains, and it's the one implemented in every major modeling application. So the comparison here because it's pretty important. The comparison here illustrates one of the most important part. So triangles versus quads. The quad meshes, as we just said, shows an organized edge loop following the form of the surface. Here, come back, Catmull-Clark subdivision. Thanks, Catmull, and Clark also. And it's applied to a quad mesh, so produces a smooth, predictable result. Instead, if you apply it to a triangulated mesh, it produces irregular, difficult to control output. So the same principle applies to rigid character, as we said, where it's deformation, and edge loops, running around a joint allows to the geometry to compress and stretch naturally. So it's very important for rigid character. Then going further into modeling, we can have hard surface and organic modeling. Hard surface modeling deals with manufactured objects, mechanical parts, vehicles, buildings, weapons, consumer products, so on and so forth. Here, the focus is on geometric precision, controlled edges in their definition through bevels and supporting loops. Boolean operations for adding and subtracting volumes. Reference to engineer specification, actually. So the priority here is the accuracy and topology that reflects manufacturer form. So this is a tool that is included in Blender, modifier stacks, also in SolidWorks, Fusion 360, and different applications. So those applications span product design, industrial visualization, and gain environment assets. On the other hand, organic modeling deals with biological, mostly biological and natural forms. So characters, creature, faces, plants, soft goods. So the challenge here is to represent surfaces that can arise from growth and biology rather than engineering. So here we can see the difference. So smooth transitions, sculpting-based workflows, and understanding of anatomy are central here. Tools that are used for organic modeling is ZBrush, also Blender Sculpt Mode, Mudbox, Maya, and so on and so forth. Sorry. Okay, and so those applications includes applications of organic modeling, including in film, VFX, game character development, medical visualization. Usually, mostly professional in 3Ds, so 3D artists specialize in one of these two main areas. Here we can see two different pictures that shows on the left a more mechanical engineered part. So on the right instead a canine form, so organical. So these two examples make the contrast immediate. You can see clearly the mechanical assembly on the left shows the characteristic of hard surface modeling. So you can see controlled definition, regular geometry, very manufactured surfaces. Instead, the dog on the right side shows organic work. You can see subtle volume variation across muscles groups, biological asymmetry, and also standing very still so you can see the tension of its own living tissues. So the differences here are not just visual, they reflect the fundamental production approaches here. Different tools, different areas of professional developments, different scopes. But we also have other kind of modeling, such as parametric, in this case, parametric modeling. Here it's very relevant on architecture and industrial design. Here parametric modeling define rules and relationships rather than geometry directly. Objects are driven by parameters. So changing a wall thickness and the whole, by changing it, the whole building will update itself. So changing a parameter will be applied along the whole building. So this enable a way of design exploration that it was impossible with direct modeling. You can also evaluate many variants quickly, very quickly, and define constraints that propagate automatically, and generate also complex forms from relatively simple generated rules. This is the basic foundation logic of BIM workflows, which are widely used in Revit, Grasshopper, Dynamo. Also, we have NURBS modeling, which is non-uniform rational B-splines, and they are mathematically inscripted. They has exact smooth curvature and surfaces. So here the polygonal mesh approximates a curve through many small faces. So the NURB surface is smooth at any resolution. So you can still go through and through and through and have still a very, very smooth resolution. So this is mainly used and matters a lot in the automotive and industrial design, where the surface needs to be mathematically exact for the manufacturing, like such as CNC machinery or press forming, that they require quite mathematically description. So the tool can evaluate at any precision. Here, the most widely used softwares are Rhino, Katia, and so on and so forth. Yeah, they are the primary NURBS tools. Also, Blender has it, but it's not developed as them. Here, we will talk a little bit still about the BIM integration, because here in Politecnico, we use a lot of BIM. So BIM extends parametric modeling with the semantic data. So in a BIM model, building elements carry not just the geometric description, but also properties. Their material, thermal resistance, structural loads, fire rating, costs, relationship to other elements like engineering. So we can also talk, when we talk about BIM, we have to talk about IFC, so the Industry Foundation Classes format, which is the standard to exchange this information between different BIM platforms that enable that exchange across Revit, ArchiCAD, and other softwares. This data richness is very valuable for integrating building lifecycle management. This creates a significant challenge for real-time visualization because they export a geometry that tends to be, let's say, poorly suited for rendering. Too many polygons, non-manifold surfaces, most of the times no UV coordinates. So processing BIM data into something that can run in a real-time engine is a dedicated pipeline challenge that we still are very developing it. And yeah, here, CAD and optimization. This is a pretty explicit one. CAD and BIM models require retopology and optimization before they're using in the real-time engines. Usually, if we think a SolidWorks software, it creates a very heavy geometry because it uses engineering precision. And in a game-ready mesh, it's very, very different kind of mesh. Because engineering precision means dimensional accuracy, so the correct measurements, tolerances. Instead, real-time rendering efficiency means polygon budget, draw calls count, and texture memory footprint. So we can see clearly these are very different requirements. And a model optimized for one is typically not optimized for the other. An assembly modeled to manufacturing tolerances may contain millions of micro facets, overlapping surfaces, and no parameterization of UVs. So by importing it directly into game engines produces usually a scene that simply can't run in an interactive frame rate. So converting such data to real-time ready assets is especially it's on its own, let's say, yeah. Then there's solid modeling, as previously mentioned, used in SolidWorks, Fusion 360, FreeCAD. It represents fully enclosed volume with physically valid properties. So mass, volume, center of gravity, surface area. So unlike polygon meshes, which allow hollow shells, solid models know their own physical properties. So how they're made. The primary compositional tool here is the Boolean operations, union, difference, and intersection. You take two solid volumes and add them, subtract one from the other, or keep only what they share. So we can see the different iteration here. So from a library of primitives and recursive applications of these operations, you can describe the geometry of essentially any manufactured object. The model is enclosed volume, so because of this, it can go directly to manufacturing. So 3D printing, CNC managing, without any additional interpretation. So let's see a little bit of the software landscape. Sorry. So this is the main landscape. The software landscape in 3D production is domain specific, obviously, in a way that but actually it's very easy to underestimate it. We can see here in the table, we mapped, and those are not the whole key softwares, but there are the primary tools. So for general 3D production and VFX, Blender, Maya, 3ds Max are very, very useful. For architectural and BIM workflows, ArchiCAD, Revit, Rhino also. Then we have industrial design, organic sculpting, real-time visualization, rendering engines, procedural generation and VFX simulation. We have many different tools. So these tools are not just interchangeable, because knowing one doesn't mean that you can pick up any other one, because they just reflect different paradigms and serving different professionals, actually. And they are optimized for different parts of pipelines. So the right software choice follows from the requirement of the work, not just from habit and familiarity. So a lot of the 3D artists, engineers uses most of them, at least one for each domain. So now we saw the modeling part. Let's go through a more specific part, which are the materials. So how the light interacts with surfaces. From the geometric representation, this part is on the field by concerning what is described. So the materials are describing computationally how surfaces looks. How do we make something look like polished steel or skin or glass or concrete? The answer actually requires understanding the physics of how lights interact with surfaces. Here we have diffuse reflection that describes light scattering that is roughly equal in all outgoing directions. So the brightness of the surface appears very consistent regardless of the viewing angle. This is the actual Lambertian reflection, I mean, after Lambert's observations. And yeah, those are usually matte materials, so concrete, paper, fabric, ceramics, and glazed, actually, ceramics. And they are primarily a diffuse material because the base color we perceived is determined by which wavelength the surface reflects. This is actually the simplest material behavior and the one that defines the baseline appearance of most everyday surfaces. Specular reflection. It describes a more mirror-like directional reflection. When a surface is smooth enough, it reflects light coherently. The incoming ray bounces off in any directions, and it determined by the surface normal, and it produces visible light on the reflection. So this parameter controls how sharp or spread this reflection is, roughness. At the microscopic level, real surfaces have a distribution of tiny facets oriented in slightly different directions. So the roughness encodes that spread, the spread of this distribution. So a low value of roughness means a narrow, sharp reflection, a polished metal. Instead, high roughness instead means a broad, diffuse highlight, like satin, brushed metal, slightly rough plastic. So roughness is empirically the single parameter with the greatest impact on the perceived character of a material. So being able to read roughness values from observation of real surfaces is a core skill in material altering. Then we have refraction and transmissions. Refraction and transmission describes what happens when light enters a transparent medium material. So the light bends as it crosses the boundary between materials. The degree of bending is determined by the index of reflection, so IOR, which encodes actually the ratio of the speed of light in vacuum to its speed in the medium, actually. So these are physically measured value, and by using them correctly in the material system, produce geometrically accurate refraction. But instead, using incorrect values, even slightly, produces it's very perceptibly wrong pattern in the refraction visible through visibility through the object. You will see the distortion. Then there's the subsurface scattering, which is a phenomenon with a substantial of perceptual impact on any surface only reflectance models that can be captured. So when the light actually hits a translucent surface like skin, as shown here, wax, marble, some of it doesn't just reflect. It enters inside the material and it's scattered around internally. So it exists at a point that differs. I mean, it's different from where it just entered. So in biological tissues, for example, this scattering happens in the dermis. So blood absorbs blue and green wavelengths, which is why the ear is backlit by a flashlight glows in red-orange color. So the subsurface, let's say without it, subsurface scattering, skin renders, they could be more likely a painted plastic. So lifeless, very artificial. So how it works? This diagram just shows the fundamental physical phenomenon underlying all the material appearances. So the white light that contains all the visible wavelengths hits a red apple. The surface of the apple absorbs most wavelengths and reflects the red ones. What reaches the eye, our eye, is the reflected portion. So what we perceive as color is this selective filtering of incident light. This is the physical basis of the base color parameter in any material system. So the spectral reflectance of the surface under, let's say, under natural illumination. So by understanding this clearly matters, it's a very practical matter. So base color maps should never contain any lighting information. We will see in a bit what base color maps are. So how we use materials in 3D modeling. We use a PBR, which stands for physically based rendering, which is a shading approach that simulates real-world light behavior using actually physically measured data rather than artistic approximations. And its standardization in the Eastern industry follows from Disney principle BRTF. It was published in 2012, which is now the foundation of Blender's principle BSDF and Unreal Engine's material system, and also the GLTF material standard. So the key contribution of PBR is actually consistency, because a material built under one lighting condition should look correct under any other lighting condition. The outdoors, indoors, no matter, under warm colors, cool lights, it's always correctly, it always has a correct behavior. So before PBR material systems, we could not actually agree on that. This shader that looked good under, like in one rendering, frequently would look wrong in another. So that's a very nice standard to have. So PBR, texture maps. Texture maps are the actual maps used inside the shader. So what gives the actual material his appearance? So the base color is a spectral reflectance of the surface. Pure color, no lighting information, and it should look correct under flat, neutral white light. And so never including shadows, highlights, or occlusions here. Roughness is grayscale. Black equals perfect mirror. So white equals fully matte. We will see it later. I'll show you the actual map. And it controls how spread and or concentrated the specular highlight is. Metallic maps is also grayscale. Black means non-metal, like plastic, wood, ceramic, skin, so on and so forth. White means instead metal. So the distinction matters fundamentally because metals and dielectrics behave differently in how they tint their reflections. So real materials are almost always fully one or the other. The middle range exists for just worn paint, oxidized surface, and transitions. Normal map instead is a RGB image encoding per pixel surface direction. And the characteristic is blue purple appearance, and that correspond to the neutral state. So it lets you to represent bumps, scratches, grouts, and so on and so forth. Then we have ambient occlusions that the dark part. It also allow you to just perceive more depth in the actual materials. Then we have emissive that makes part of the surface emit an actual light independently of what's illuminating them, like screensavers, neon signs, LED indicators, and so on and so forth. Okay, here we can see the actual base color. So the images just put in the materials system in concrete terms. This is a stone surface and it's decomposed into its constituent just color. As you see, it's flat. Here we have the roughness map, gray from white to black. We have normal map, metallic map, displacement map, ambient occlusion map. And here we can see the actual material behavior in the 3D space. You can see the row-based color texture and the fully rendered PBR sphere illustrates the actual contribution of each layer. The first one that I showed you, the base layer. So that's actually a sphere that has no geometric complexity. So just his subdivisions. And its three-dimensionality, it's made by all those maps combined and the rendering system that it's evaluating them. So here we have same geometry, same materials, just a big difference. The difference is the rendering, and it's how accurate physical light is simulated into the render. Here, nothing on the three-dimensional description of the scene. It's just the visual consequence here shows up is how it's rendered. Lights has bounces, surfaces to illuminate into one to another. A renderer should behave like soften shadows edges, the ambient feel that makes shadow areas feel lit rather than just simply dark. This phenomenon come from the physics of light transportation, not from the geometric or material complexity. So this is why the illumination is the dominant variable in the rendered image quality. And that's why we examine the rendering algorithm constantly to compute them in the next parts. So how rendering actually works. There are different types of renderings. We have rasterization that projects scene geometry into the 2D screen and determines for each pixels which surface is the closest to the camera. Illumination is computed locally using material approximation, and it's extremely fast. Then we have ray tracing, shoots rays from the camera through each pixels. So where they hit a surface, they spawn reflection and refraction rays to the same. The result is pretty accurate shadows and reflection. It's more hardware expensive than rasterization, but right now we use it a lot in real-time context thanks to GPUs. Then we have path tracing. It's based on full Monte Carlo simulation of light transport, as we told before. The rays from the camera bounces around the scene and statistically converging into the physically correct result over all the samples. That's used by Blender Cycles, Arnold, RenderMan, even Blu-ray. So that's actually a computationally very expensive. 100 of 2000 samples per pixel needed to just have a clean result, but it's physically accurate. Then we have under-hybrid real-time, such as a software that uses its Unreal Engine 5, Lumen, and that combines actual rasterization for the primary visibility with a selective ray tracing for indirect illumination. Here we can see the different rasterization methods: rasterization, ray tracing, path tracing, and lumen. And the panels just show the same scene rendered with different algorithm. So from the cheapest to the most accurate one to the actual hybrid one. So why we use those kind of algorithm? Because the light is very important in our job. Let's say it accounts roughly 70% of the perceived quality of any render. I mean, geometry and materials are secondary than lighting. I mean, this is an empirical claim, but with a strong support in professional practice. We can see the human visual, I mean, the human visual system is highly sensitive to the properties of light fields. So the distribution of luminance, the character of shadows, presence or absence of interreflections, I mean, we can detect lighting errors very, very easily. Here we can also see a very simple 3-pointing lightning, key, fill, rim, which are the foundation of lighting setup for both photography and 3D renderings. The key light provides just the primary directional illumination. The fill light reduces the shadow contrast without just eliminating them, controlling the ratio, obviously, between lit and dark areas. And then the rim light separates the subject from the background through a contour light. Then we also use HDRIs that we apply them as environmental maps. They contribute to have a physically measured light energy from every direction into the 3D space. It's by the resulting illumination reflects the actual spectral and directional distribution of light of the environment. HDRI lit renders tend to integrate more convincing light interaction with the context than artificially constructed directional lights. So we use it a lot, a lot. So how to compute those lights, those materials, the meshes? We need rendering engines. So I will do a quick map to a rendering engine landscape. Here we can see an image from Cycles rendering engines, which is a full path tracer. So it's physically accurate. It's also free. It uses CPU, GPU, even both in their backends, and is used. I mean, it's used when the output quality matter most than time. Then we have Eevee, also from Blender. It's a real-time rasterizer. It's used in animation previews, motion graphics, and any context where the actual speed take priority over physical accuracy. Then we have Unreal Engine with Lumen that implements hardware accelerated hybrid global illumination. It's real-time lights dynamically updating, no pre-computed light maps. Then we have Blu-ray and Arnold that they occupy commercial and high quality space. And Blu-ray is mostly used in architectural visualization. We have Keyshot, same thing. Arnold And here we can see the table that summarize the relationship across the engines for type, speed, quality, and typical use case. As previously mentioned, for 3D modeling softwares, match the tool to the requirements. So speed versus realism, the core trade-off, offline rendering perform full path tracing, minutes to hours per frame, non-compromises on physical accuracy, but it's used for still renderings. Instead, real-time renderings target around 60 to 120 FPS, so it needs a way faster rendering time. It needs but a lot of implementation and optimization. So the line between these two is right now narrowing, so it's just hasn't solved yet, but the convergence, it's pretty miserable. So we hope very, very soon that we will use real-time rendering as a path tracer. Here we can see the different type of light interaction as path tracer, ray tracer, and rasterization. So it's pretty visible. So why optimization matters? VR is a minimum frame rate of 90 FPS because of the vestibulo-ocular reflexes. This is the mechanism that stabilizes gaze during head movement, and it operates on 10 to 15 milliseconds timescale. So when the rendered image doesn't update within those kind of time frame, we will have motion sickness, or also called cyber sickness. So this is a physiological constraint for us, not just quality presence. Then we have standalone headsets like MetaQuest 3. They don't have enough GPU capability. They have like a roughly GPU capability of a mid-range smartphone. So an optimized scene won't run on them. So we need to optimize them. And we have industrial AR application, welding, guidance, assembly, maintenance. Those kind of application need a very small latency, even few seconds. It's a safety concern. And we will finish with web XR and cloud-based 3D visualization that bandwidth and memory constraints are the hard limits. So geometry optimization, we'll go very fast because it's very late, and I know that it's late for everyone. So what we use for geometry optimization, decimation that reduces polygon count algorithmically by collapsing edges. And it's guided by a cost function that minimizes deviation from the original surface. The most common algorithm is the quadratic error metric decimation. Then we have the retopology, which is the manual reconstruction of a clean, low polygon mesh. We have LODs, level of details, so we all have different details, maintains the multiple versions of an object at the different polygon counts. We have instancing render as a single mesh. It's multiplied many times with a minimal additional cost. That's essential for like instances like vegetation, crowds, architectural repetitions. Then we have mesh culling that skips just rendering geometry outside the camera fostrums, just hidden behind other surfaces. So that's pretty cool, actually. Texture optimization. So texture, it's often the dominant GPU memory constraint in complex scenes. Main strategy, 2K is the standard for most real-time assets, 4K for hero objects, close camera proximity, 8K only for cinematic or still rendering contexts. And the dimension must uses the power of 2 if it uses Unreal Engine for GPU compressions. Texture atlas packs multiple object UVs into just a shared sheet. Then we have compression. PNG is lossless and large, used within the production pipeline, but not for deployment. So we use BC7, DXT, or just GPU native compressed formats. It's 4 to 8 times smaller than an uncompressed PNG. So here you can see two different, one on the left, it's unoptimized geometry with an unoptimized image texture. And instead on the right, it uses actual my algorithm. So I'm pretty happy about it. The optimized mesh. Texture optimization, just said that, sorry. So CAD beam photogrammetry optimization, we talked a little bit before, but I think we don't have time for this. So photogrammetry produces an extremely dense mesh, typically 10 millions or more polygons per object. So no clean topology, UVT parameterization, photographic texture that includes the illumination. So we need to actually just optimize it. Optimization, it's very, very helpful to a VR ready asset. Here you can see a processing, my algorithm that processes those photogrammetric surveys. We can see that we went from 44 million space count to 3,000. So a reduction percentage of 99.99. So pretty huge. Texture size, diffuse, which is the base color, and normals, 52%. FBX size, 99. So we can see that optimization matters a lot. So the future, AI-assisted modeling and generation. This is the actual final section. We have different tools, and it's a wide range of tools. So it's very hard to just select one. Example here, text to 3D generation produces 3D geometry from natural language that we use a lot. We described an object using, then it will generate a 3D object using generative neural network. It has been commercially deployed within the tube last year. Those tools, like this one is Tripo, but still, the quality evaluation is still to be assessed. So sometimes they make very good objects, sometimes still not. And sometimes they just have irregularities, UVs, inconsistent UVs, or topology not reliable at all. Then Gaussian splatting. Here you can see the two different a comparison between point clouds and Gaussian splat. Gaussian splat result is nearly photographic. Instead, the classical point cloud is just digital. So for cultural heritage documentation, making physical artifacts accessible through this immersive experience, this quality gap really matters. Then we have AI texturing, Substance 3D. So Adobe is implementing them a lot. So what it does, just create different kind, or it helps the actual 3D artists to produce texture maps in way more efficient way. Then we have AI in the production pipeline. So here we have the DLSS. A lot of you will just recognize it. So we can just reconstruct a high resolution image from a lower one. And it's very competitive seems with AI, just add details, depth, and so on and so forth. So just to see a little bit of those final rendering different platforms. Here we have Unreal Engine that we use it a lot in game as a gaming engine, virtual production, so on and so forth. Then we have NVIDIA Omniverse that implements USD, so a common ground for all the main platforms. XR that is right now convergent to AR glasses that are quite blurring the boundary between the physical and digital in everyday environments. So real-time guidance, information, trajectories for robot welding pots overlaid in physical machinery through AR glasses. And as final, we have digital twins. So real-time synchronized 3D replicas of physical buildings, infrastructures, and industrial machine. They are still now in active deployment. So it represents BAM integration into real world. So yeah, real-time 3D representation of physical infrastructure that update continuously as physical system change. So I think that's it. I'm sorry for cutting off the last part, but I know that the presentation can be very hard to follow. So I will ask if you have any question. Can you, where is it? And thanks a lot to everyone. I can see, I went through everything. Okay. Thanks, Oscar. And I wish you all the best. And thank you, everyone. Have a nice rest of the evening. And I hope this presentation just was what you wanted. Okay, I will now go through. Let's see where I have to. I can open. Okay. Bye-bye, everyone. Ooh. Thank you so much. Okay. We'll stop.